General relativity, step by step. Last time I was discussing the fact that the radius of the universe is much larger than the largest structures observable in the universe, which justifies our use of a universal fluid, which we've got here. So it means that I'm going to ignore the small scale structures and small scale phenomena occurring in the universe. So I'm just going to consider a universal fluid which is uniform. What I'm going to do now is to introduce a whole bunch of, two assumptions which make our lives mathematically much easier. I'm going to introduce the assumption of homogeneity, and also isotropy. Homogeneity means it's the same everywhere. The universe looks the same to everyone, and there's no sense in which some places of the universe are central and some are peripheral. Everyone in the universe basically sees the same thing. Sometimes you see it called the principle of mediocrity. Everyone's pretty much the same, and that's a very appealing assumption to make. It certainly makes the mathematics a lot easier, but it's also quite a nice sort of philosophical starting point for cosmology. And it also seems to agree with observations that we can make about the universe. Isotropy is the same in every direction. It would be conceivable for us to look in a particular direction on the celestial sphere and see one particular set of phenomena, and if we look at 90 degrees to that, we see a different set of phenomena. And that doesn't appear to be the case. It's consistent, it's possible, but it doesn't appear to be the case. As it turns out, if we actually observe the cosmic background radiation, the microwave radiation field, we do see a dipole moment because the galaxy, our own Milky Way galaxy, is moving with respect to the cosmic background radiation. But that's a detail. That's just our little galaxy in our little local group, which has got some particular local property which I'm going to ignore. So what I'm basically going to do is to assume that all our observers are at rest. And that's a very justifiable assumption because of course if you're moving, because the universe is expanding, as I'm sure you know, if the universe is expanding and you are moving very quickly, you're moving at sort of 90% of the speed of light with respect to the cosmic background radiation, then pretty soon you will come to the land where everyone is moving at that speed and you'll be at rest. So the universe expanding acts as a sort of cooling, it's got a cooling type mechanism which enforces this assumption here that all our observers are at rest. There's just one other assumption which I want to make, or I want to discuss, and that's the steady assumption. That the universe is the same at all times. It's unchanging, I guess. And this is again a philosophically appealing assumption, but it appears to be wrong. It appears to be incorrect and inconsistent with observations. It's nice to assume, and maybe I'll talk a little bit about steady-state cosmologies, but I'm not going to assume that in the majority of this screencast. I am going to assume homogeneity and isotropy, and I'm going to use a universal fluid as well. I'm going to stop there, and I'll develop some mathematics, or the mathematics that follow from these assumptions, in the next screencast. Okay, stop.